Good evening, everybody. We are starting our next set of series of webinars from our system engineering group of Urth Electronic India. And this is the 6th webinar we are holding. And today the topic is system thermal management. And a couple of guidelines before we begin the webinar is kindly mute your audio. And also, if you have any questions related to the webinar, please type it in the chat box. We will answer all your technical questions at the end of the webinar. Arun Kumar will answer the questions. Any other glitches that you have, please type in and we'll try to take care of it. So before we begin the webinar, I would like to briefly tell you about our company, Urth Electronic India. Urth Electronic India is a part of the Urth Electronic Group, which is a subsidiary of Urth Group Global. Urth Group is a family-owned business from 1945, and they have a presence in 80 countries. They have close to 80,000 employees. And Urth Electronic is a subsidiary of Urth Global. They are headquartered in Hiddenhall, Germany. They have around 7,200 employees worldwide. They have 14 production locations, and their turnover for the year 2020 was 823 million euros. Now, Urth Electronic India, the next slide I'm on, is they are a number one partner. They are a number one partner in PCB and PCB-based solutions. We provide one-stop solution to all electronic device developers and manufacturers. We also have comprehensive solutions right from concept, like you can see, from the design to the serial production. And we have expertise. We have engineers in the CAD and CAM field. We are located both in Bangalore and in Mysore. Now, in the next slide, we'll explain to you the different divisions of Urth Electronic India. We have 4 business units catering to different aspects of PCB and PCB-based solutions. We have the Circuit Board Technology Business Unit, System Engineering Group, Computer-Aided Manufacturing, and Intelligent Power and Control System. In the system, in CBT, we basically, cater to prototype engineers, developers, manufacturers, and different kinds of PCB boards. We supply them. We also have quality checks on the PCB boards, and we also buy and sell very standard PCB boards and multi-layer, up to 30 layers of PCB boards. We have also different kinds like the flex rigid and complex boards. In the system engineering group, we are basically we have CAD engineers who do the layouting and testing. We have different expertise in signal integrity, power integrity, thermal analysis, library management, and so on. Computer-aided manufacturing, we basically give Gerber output for production ready data to our main business unit, that is in Germany. And intelligent power control systems, we provide PCB-based solutions for power boards, electronic controls, and for high electrical output and very compact, very lightweight components. So we would like to also explain to you the growth of our company. We have grown, in the next slide, we have grown from 10 employees in 2005 to 200 plus employees in 2017 onwards. We are very happy to say that we are ISO certified in CAM, CBT, and SC division. We have acquired the IATF certification for our ICS business unit. Next, we will tell you briefly about the circuit board technology. We are leaders in PCB and PCB related services. Urth Group Global, the main company, believes really in good quality products, and that has trickled down to all the subsidiaries and companies throughout the company worldwide. So whatever boards that we provide to our vendors, customers, are all quality checked And we also have engineers who also do signal integrity and different kinds of heat management and design factors. We also check and promise good qualities for our customers. The next slide, we are system engineering group, where this webinar is presented from. We have domain expertise in RF design, layout design, thermal management, EMI and EMC expertise. We also have very good engineers in simulation of signal integrity, power integrity, and thermal analysis. We believe in doing things right the first time. In the next business unit, the intelligent power and control systems, like I said, we give solutions for power boards, display and control planners, electronic controls. We have very complex components which are also compact in size, have less weight, and have good resistance to environmental conditions. And they are quite, unique, and they do a lot of functions given the size of the component. And the main market is the automotive sector as of now. So then the next slide, Arun. We have the computer aided manufacturing. Like I previously said, they do have expertise in high-speed PCBs, capabilities, CAM capabilities in rigid flex and flex board designs, motherboards, backplanes, evaluation boards. We also design help in complex multi-layer boards. We basically get the data ready for production. That is the main function of the CAM group, which is mainly based in Mysore, and we have a few of them also in our Bangalore location. So our presentation is from Mr. Arun Kumar. He has over 10 years of experience in this field, and he will be talking mainly about the system thermal management. Like I said, what is thermal management, why it is important. We know that nowadays the boards are getting smaller and a lot of components are being fitted on the board. There is a lot of issues with signal integrity, power integrity, which we have already had a webinar before. And this creates a lot of heat flux on the board and a lot of harsh conditions or variation in temperatures. So he will go through all the cooling systems, the heat transfer, what is the role of a simulation engineer in thermal management, and also give you case studies on different scenarios. So now I will hand over the webinar to Arun. He will take it forward from here.
Good evening, everyone. First of all, thank to Ms. Kamala for the brief introduction about me and our organization. So now, in this session, everyone has thanks for the registration who and all attending. And this session is system thermal management, which is nothing but electronics cooling. So we have conducted the last month about the PCB thermal management. So this is about thermal. From the continuation of that, we have done now for the system level thermal management. So in this system thermal management, what is the addition from that PCB thermal management, and what are the why the electronics cooling is needed for our current design or a model, and what type of heat transfer about the basic intro, what and all we have to consider here. And what is the role of a simulation engineers? Because this field is different from other simulation. If electrical engineer work completely, electric and electronic engineer completely work in a layout and other hardware parts. But in the thermal simulation, we need to know about electrical, electronics, as well as the mechanical thermal part. So how this simulation engineer play a role, and how that workflow work. So that we are going to see here, because here the simulation engineer has to know the two things. What is the power dissipation, and what about those components we have to using, and how to take away those fluxes from that particular component in the enclosure part, in the CAD, mechanical CAD thing. So now, as she said, we are the ISO company, we have to follow some workflow. I will explain the system thermal workflow using the simulation and what is the thing. Then follow up. We have few case studies for the explanation which are related to the heat transfer, whether it's a simple heat sink to a complex heat pipe cold plate techniques, and what are the things, how it effectively we can implement in this in our system, or it should not be under design, it should not be a over design, it should be optimal design. So that's why the simulation play a vital role, even if experimental mechanism is there. Plus, I will give some few introduction about why the simulation and when compared to experimental. So everybody know there is a no replacement for experimental. Still, we need a simulation must when compared to the time with respect to experimental. So those things we will just look into that thermal tool session. Plus benefit of the simulation. So now we'll go into electronics cooling. What is that? So here, the electronics cooling is nothing but we have a system which contains so many components, so many racks of PCBs, so many internal and external with related to the electronics will be there. So we have to maintain at an optimal temperature to perform well. So that is the main role of electronics cooling. So that's why the name itself mentioned to cool our electronics things. So why the electronics cooling keep on the need of the electronics cooling is increasing, because there is a high rise in the power density as well as the clustering of components. So many high power components are now we are going. Now we are using nowadays when compared to the old days. If you compare the 10 years back, the power what we have used and now what we are using and consuming, it's totally different, and we have a special techniques to take away those flux from there. And so here the clear goal for thermal management, how it play a role is, we have to remove the heat flux from the particular component. The power dissipation itself even high. If you distribute the heat properly, automatically the flux will reduce. So we can maintain the optimal way to keep the temperature in an operating condition. So next, in our system design, apart from the PCB design, because PCB itself, if you the bare board and the component, if you kept outside of the ambient, the temperature will be different. And the actual condition where we are going to use, we have to take those ambient conditions as well as where we are going to place inside. Suppose if it is automotive industry, the component will be placed inside the hood or inside the cabinet or inside our driver cockpit, like that. If it is a consumer electronics, if it is a handheld, or we are placing inside some of the consumer goods or a biomedical thing, whatever the thing, we have to make the temperature under the control for the particular component plus the overall system while we when we are placing those subsystem into our complete system. So that is the design parameters we use to drive and how to maintain those optimal temperature. So that's it. The way we tackle in this design challenges is only through our special care we can take, whether we have to use a forced convection or a free convection or a different cooling techniques we have to use. So that will prevent from our warranty period when come to overall cost. It will reduce our overall design cycle time, and also it will probe in detail when compared to the experimental. So now I'll display the simple chart, the importance of electronics cooling. So if you see this chart, this is familiar to most of the people. You people know almost the 55% of the failure because of the temperature when compared to dust, humidity, vibration. Next, the important thing is vibration. So here there is our thermal simulation engineer also having an important role between PCB layout design, like electronics engineer, as well as the structural engineer, mechanical structural engineer, because the thermal parameter affect both the functionality of the component as well as structural deterioration. So that's why the temperature, the simulation engineers play an important role so in this electronic criteria when compared to that, and we should have a knowledge in both the sides. So plus there is another chart which will show over the year how the wattages are increasing with respect to the performance with the heat. So I'll go on to the next slide. So here, so we have a system. So there is a picture here. So we have the system, we have the component, and the PCB we have placed inside it, and we have attached the material with the tent closure. So here you can clearly see the heat is arise inside. The heat is much. The red indicates higher side. The blue arrow indicates the lower side because of it's an ambient. So inside the system, the temperature is higher. Why? Our right cooling strategies, which way we take out those temperature. It can be suppose that's why we segregated as a PCB thermal and system thermal. So here PCB thermal, we can do three different things. PCB thermal is nothing but here component level I have mentioned it. System thermal is nothing but that enclosure level I have mentioned it here. So now we just give a brief about PCB thermal. So how we can reduce itself in a PCB? What we can do? We can increase the layers or using a vias. So a conduction path for that particular component, whether it's a MOSFET or an or a IC. So how we can take out the power? So here there is a correlation is the thermal interface material we are using. So we have a processor here. So we have to take out from the case to that enclosure. So enclosure here I'm showing the plain enclosure. It might be a heat sink there. So in our case studies, so these information we will discuss one by one. So which type, whether we are using a force type for this particular thing, or we are using a free convection, or we are using a heat pipe or normal heat sink for the individual component, then we take out heat sink of the enclosure for the other component. So those things will play. Why? Because once we control the temperature using which we start from the PCB level and ends in a system level. So it's not a separate topic. So once we are developing a product, we should not only think about the PCB. It's a correlated because we should not placing the too much the highly heat flux component near to the area. For example, if you're taking a 10 by 10 mm, 10 by 10 centimeter board, for example. So in that board, we are clustering at the one point, that is 1 by 1 mm. We have accounted the 10 watt of power in that particular area. The temperature will shoot up. That means the heat flux over that area is higher. So we have to distribute the power. From the distribution, the board itself has to happen. Then it forwarded to the system level. We have to take away those further heat reduction through that enclosure heat sink or using cold plates or heat, depend on the powers. So here there is a criteria we have, whether it's under design or over design. For a 10 watt, we should not use the heat pipe. For 120 watt, we only natural conduction is not enough. Depend on the fluxes. So that's we are going to see in the further slides. For a basic understanding for the people who are new to that this topic, we have three type of heat transfer. The conduction, convection, and radiation. Apart from the conduction, convection, radiation, we have another type for the electronic engineers we face is Joule heating, which is nothing but I square R loss. So that is the one we have to account including. So here the black arrows indicate the conduction path. The blue arrows indicates convection and radiation parts. So here it's clearly defined the conduction between the object to object where it touches. The convection and radiation, even if not touches also, the heat transfer can happen. So this is the basic understanding. You just keep in your thing. So now the green is the PCB. The in between gray is the component or IC. Then further on the top heatsink. So it has to take heat in a two-way, the bottom as well as top. Top through the heatsink, bottom through that vias, or if we have some thermal pad or a conduction kind of a thing, that will work. So now we will move to the next slide. So here the simple thermal management scenarios I have to explain before going to a case study. So how we can reduce, how we can distribute, how we can account properly. So those information. The first the main goal I said is uniform distribution of the flux, as well as how much removal of the flux from the particular component which transfer to a enclosure or to the other sites or subsystems. So that one. So how to reduce those thermal resistance between the components. So if you are attaching, if you have a component here, so I am explained with the two things. One is the gap filler, another one is the heat spreader. For example, you take it. So here we have an IC component in the black area. So from the IC component, you have to transfer heat from this IC to that enclosure. So in the gap filler, you have a very rich concentration of heat over this when compared to the heat spreader, because it spread the heat. We distribute the heat flux through the complete enclosure. Here we are not distributing the heat, only transferring the heat. So that too, how we have to transfer is all the material have some waviness over the structure. If you see in a microscopic point of view, see here, the bad interface, good interface, the below picture is there. So the bad interface, if you see by the, even if you in a bare eye, if you look, the component will be the smoothly finished. Even if you see in a microscopic view, there will be a waviness, similar kind of a heat, similar kind of here. The cooling assembly and hot component is there. So in the hot component is nothing but our IC. The cooling assembly is nothing but our heat sink. If you see in a microscope point of view, there is a waviness. To fulfill this waviness, because here the air gap will be there, the point of contact is not clear, so it will create a resistance. So if the resistance is created, how to avoid this resistance? We have to use a proper, even if you're using a gap filler or a heat spreader, here we have to account the thermal interface material. So these are the components we have to account when we are doing a system thermal management. It starts from the PCB level, it ends in a system level. In a PCB level, we can increase the conductivity, increase the copper layer, how much, wherever it's needed. We can place a thermal bias. We can expose the area using this heat spreader, or in a board level, we can make a big pad area which exposed to the air, which create through a convection or by a conduction, whichever it's touching, and we can use it. And here these thermal interface material also, component to component, it can happen without electrically conductive kind of a paste itself. It's available now, so we can use that paste. And now we'll go to the next slide. So this is already I have said, this picture I took from the previous session, which is done by Mr. Raghavendra. So here we have a set of engineers which play a role to design a system and develop a system. So it starts from a circuit engineer, then come to mechanical design engineer, PCB design engineer, then software engineer. So now I'm arrowed for myself, the mechanical design engineer or a thermal simulation engineer. So my objective is heat dissipation design of housing, how I can dissipate through my enclosure. Even they designed the board PCB with the layers, and those information in the further slide I will explain what are the things we have to consider it. So here my main objective, I said, is how to distribute from the PCB or from the component, how I will take away those heat, how to define a flow path from the bottom of the component to the top of the enclosure through the housing, what type of material I can use, how to reduce the thermal resistance, that is touching of the two components, and how we place it, what way it has to place will reduce the temperature. So it should not be closely clustered, and now there is a form of miniaturization of the component. The how will play a role. It should not deteriorate in a structural manner. It has to account those components. Plus, what type of material I have to use for the particular temperature, whether it's a desolder or in a manufacturing point of view, it is acceptable. I can design anything inside a simulation, but it should be manufacturable. So those areas we have to think and design it. So that's why we start from a PCB level. From the PCB level itself, we have to think whether it can accommodate with the system. If you're going to place in a system, those areas, key areas, are critical components. From there, we can take out heat to that enclosure, because someone is designing the board, and after we are designing the enclosure, in the sense we can't accommodate. So from the day one itself, if we start how we are designing the enclosure and how we are placing the component over there, whether those the flux are distributed properly. Those information if we have done, then our things will be easy. So here the understanding of the mechanical engineer, if you see, he has to know the information what we have to get from the circuit engineer, from what he has to transfer to the PCB engineer after the results, whether it's a contour or it's values they want to meet it, whether it's 100° or a 120°, and also to the designer or a manufacturer for the client, whether it's a manufacturable or not, if you design an enclosure point of view. For example, the fin type, which has to reduce the cost. So now, this is those correlation flow, you can see it. So here there is a board level. I have segregated in a two part. So one is the board level, the second one is the system level. So in the board level pre-layout, how many layers we need? You can see in that bubble. So these are the question we have to think. How we can reduce? We have the component for that particular temperature. We can iterate these things inside the simulation. So you can change the stake up. You can increase the copper layer, and you can increase the copper layer thickness. You can place the vias, whether it's a filled vias or it's a normal via, or how to distribute the component. So once you are distributing in the right hand, another powerful component will be distributed in the left hand. So the flux distribution and the cumulative power will come down. And for the particular component, heatsink is necessary because it will add up the further cost as well as the further weight. So these are the things we have to consider from the board level, because without considering the system, we put a heatsink over that particular component, but actually from the enclosure also there is a heatsink we can provide it. So how we can make it, how we can reduce the time cycle, we have to think and we have to work. So here the workflow clearly indicates we have to do a pre-layout thermal to define the layers and thickness and those properties, vias properties. Then the layout has done. After the layout, everything, the component placement for the component placement, the whether within the limit or not for the complete thing, then it will go to the mechanical people for that out layout. They will make an enclosure. So with the enclosure and the board, for that, for our ambient condition, some people need for 45°, some people need for 55°. So we will go for a 55°. If it is an extreme condition of 55°, we can use for the 55° condition. With that, we with the enclosure, the complete analysis can done. It goes for the final assembly or in the manufacturing. So this is the relation between board level and system level. If any changes in the system level, then it again come to a layout engineer. You want to modify the things. So this will happen. So so we are the ISO certified company. This is the workflow we used to follow. So from the board level, we will start and we will take the data. Then we place those board in a system. So what type of system we will do a geometric cleanup. So these input, which is nothing but meshing, modeling and meshing. So here there is a flow in the below. You can see it: modeling, meshing, solving, post-processing. This simulation is nothing but general CFD. You people know. Modeling is and meshing is nothing but pre-processing. Solving, second part is the solving. The third part is the post-processing. The modeling and meshing, the pre-processing itself, it took 60 to 70% of our time, because we have to clean up the model, prepare the model for the simulation. Why? Because we should not how we say, if you have an actual model, we should not more deviate from the actual model. How we can replicate inside the same model for the simulation, that we have to think and we have to implement. That is the main role for the simulation engineers we have done. So for the cleaning and inputting powers, analysis, condition, metal properties itself, it took 70% of our time. The solving will do by the computer. So nowadays with the supercomputer, we can go with it. So then what type of problem it is? We will do a study if there is an improvement or we can do it further. Then we go for a meshing, solving, then post-processing the complete thing. What are the information you need from that? For the particular component, what will be the temperature? What is the case temperature we have to maintain? And which way it can take out the heat for the particular area? Where is the hot spot? Those information will get it from the post-processing. So this is the workflow we used to follow, and this is the generic workflow of the CFD. So now move to the next one. So now we have the case studies. So we have three case studies. The first one is the traction controller. The second one is the smart projector system. The third one is the 5G base station unit, which is placed over the antenna. These are the design criteria given by the client. The first we will see about the traction controller. So traction controller must not exceed the temperature of 100 degrees Celsius. That is the first thing, the overall system. This system has to run with the 3 mode, 2 mode in steady state condition and another 3rd mode in transient condition. For this we have to design an enclosure with the satisfaction of 100 degrees Celsius. So this is the design criteria for that. For a steady and transient, which is nothing but steady is with respect to time, there is no change in the condition, is nothing but steady. With respect to time, there is a change in condition, change in the power with the step input or linear input. So that is nothing but transient. So first we will see the details of a traction controller. So we have a traction control. You can see the board. This is the enclosure, and this is the board front and back side for the information I have shown to you. So here, what are the inputs we considered? The first thing is for the system thermal analysis, we need input of all the PCB details, which is nothing but the ODB plus, as I have shown in that workflow. We need a ODB plus file, step file of this particular component, and what is the power information, and what is the metal properties. Apart from that, when we are compared to the environmental condition, whether it's a forced convection or a free convection, or we can also analyze and we can predict it, use it. That also, the last case is that I will show that one. So here we have a forced convection of with 5 meter per second, and for a steady state we are using a two mode, which is a 30 watt mode and 72 watt mode. For a transient power, 80 watt mode we have. So here the enclosure is the aluminum enclosure. We have used it, and the black blocks, the 12 block, the black blocks are there, right? Those are the MOSFETs which are power up here. So you can see the result for the 30 watt. There is a maximum temperature here. The limit is 100 degree. So we have ambient of 45 degrees Celsius. You can see it in the graph. 45 degree, it reach up to 64 degree for 30 watt condition. So this is in the board side. On the left side you can see this is the board layer. For that enclosure, we have the maximum of the temperature around 54 degree. You can see. Sorry. So next thing is 72 watt. So 72 watt, what is the temperature on the board as well as enclosure we have to think. So here we have do the two things. We started from the PCB level. So we distributed the power instead of placing at the one area, we distributed across the board from end to end. So we can distribute the flux. We have to keep the remaining component as well as this component, which is the best way to can distribute. So this is the way we can distribute it, which will be with the limit of 100 degree. It should not exceed 100 degree. So now for the 45 degree condition, the maximum temperature, the case is 92 degree on the board. It is coming. For the enclosure, it will be around the same, the 74, 68 to 74. So this is for the transient condition. So I will show this. So you can see it here with respect to time. You can see on the top left corner there is a time. So we run for a 40-second condition. So for a 40 seconds, the maximum temperature reaches here. You can see it here. So maximum temperature of getting 60 degree for that 80 watt transient condition. So this is the way we can do. So here the simulation, we can simulate for steady as well as transient. That will be that way it helpful very much, as well as you can probe anywhere. Whatever the component you need with respect to the time, you can stop anytime and you can see the result. So this was for 60 second model with the temperature condition. Further, if you run for the furthermore 20 seconds, you can see the results from that. So now the second one is the smart projector system. So a smart projector system, you can from the image you have seen, this is like an Android build projection system. So you can install any software over here. You can act this as a webcam for any application, and there is a speaker, there is a mic they are developing. So this is a LED smart projector. So you people know LED is the highly heat generating component. Almost 80 to 70 to 80% of the power will be dissipated as a heat. So here there is a heat spreader. From the picture you can see there is a heat spreader, and these are the three LEDs over here, and there is a heat pipe which is attached to the heat spreader. Then it goes to the heat sink. Then it is taken away by the blowers fan. So now what is the condition for this case study is this maximum temperature should not exceed 75 degrees Celsius. So this is experimentally we have verified, and we have compared the result with the simulation, and there is a one good point here. And here they are using a liquid cooling technique, which is nothing but a heat pipe over here. So instead of a normal heat sink, for controlling the temperature less than 75 degrees, they are using a heat pipe. And one more thing is, as already said, this is a smart projector system. So it has a mic and speaker. So once the blower start, the increasing temperature, this is a varying fan. So with respect to the temperature, the fan speed will vary. So we know the minimum and maximum CFM. Once the fan started the higher CFM, it started the buzz sound over that mic. So after hearing the mic, there will be a sound, and even if you place a noise cancellation mic and all the things, still they are facing an issue. So we have to identify where those turbulence is happening. So that also we can identify it in this case study. Plus, how we can reduce the turbulence using a front grill for further cooling purpose. So here, the advancement is we are using liquid cooling techniques. The second one is with the fan running, we are accounting how much CFM we have to use and how to reduce the turbulence for the complete system performance. The second one is where to place a grill to make to reduce the turbulence, make a airflow streamline. Now we go into the projects. So here we have done for a 45 input condition is 45-degree ambient with the force convection because the blower is running, and we have the fan curve setup. This is the fan curve we have used for that. Plus here we have used fluid as air and fluid because heat pipe has water. The total dissipation is 120 watt here. This is the over after analyze with this condition, we have get the temperature, we have reduced using all the inputs get it from the side of the heat pipe, and how we have implemented with the effective conductivity in the particular heat pipe area, as well as the material we have considered for the LED and other structure. This is the LED assembly plus heat sink. So here we have maintained the temperature of we have achieved the temperature of 70-degree with respect to that, plus with the ambient of 45-degree condition. So now we come to the second point. The second point, if you see the velocity of the flow, which is nothing but the cross section, you can identify from this picture how I took this picture. Now you get it. So this is a picture which is the cross section of the thing. So now we'll move to the same slide. So here there is a turbulence in the particular area. So here it marked as a blue color. So here there is a dead zone which create a circulation. This circulation will affect our noise of the mic. So how to avoid this circulation? That is the second objective when modeling the system. So here you can see it here. There is a circulation here from this is the airflow path over the thing, over the system. So everywhere it is streamlined. So in front of the lens there is a circulation over here. So how to avoid this circulation? So we implemented where to place a grill. We iterated over this thing and we implemented fan grill over here. So without grill, you can compare the picture and you can see it now. So first system is without grill. The second system is with grill. So without grill, there is turbulence in front of in between heat sink and lens area. With the front grill, there is a no much turbulence over here. There is a streamline flow in the particular area which reduces the turbulence as well as which reduces the noise in the mic. So this is the second point also we have achieved from our analysis. So you can see the turbulence point of view with the cut section here. So with the drill, there will be a no blue zone. This blue zone is nothing but because of the turbulence, dead zones are created. So no turbulence, it's a clear streamline flow. The distribution of speed of the wind is clear over here. So when we are doing this kind of a thing, so here we have achieved how we say, we have achieved the two things. One, we have within the limit we have controlled it. Apart from the electronics thing, even for the fluid characteristics also we have accounted. So where to place a mic, and if we place without dead zone, it will it will enhance the performance of the complete system. So further we have to take into the thing is the overall system. If we add some more processor, because it's a smart projector system, as I have already said, well, suppose once you place another set of a board, a processor board over there, it may heat up further. So once you heat up further, I have to play a role with the enclosure. So what kind of material we can do. So these kind of steps, if you do with the actual workflow, like without simulation, we have to assemble it and manufacturer the cabinet. It goes to the testing again. If there is a shoot in the temperature of the particular thing in the thermography, then it will come to a system level. We have to correct it, then do it. So if actual design cycle is a 10 month, so in a simulation we can done within a 1 or 2 month. Within the time we arrived what we needed actually, and also I said there is no replacement. I will explain in that further slide why the reason is. So here the third one is this is the base station unit for 5G. So now we have to see the condition. What are the conditions we are using here? So here the overall temperature must not exceed 120 degrees Celsius. For the extreme condition, extreme ambient condition, they used 55 degree as a ambient. So what will happen if it is a free convection? What will happen if there is a forced convection? And here the catch of this system is, so earlier the last two systems we have only one PCB over there, even in a traction controller and in a small projector system. In this base station, we have the 5 set of PCB, 5 rack assemblies will be there. We have to take away all the heat from there and transfer to the enclosure, and how well we have distributed the flux, and where we have to place those rack of assembly of the PCB. Because we can't place one over one. We have to distribute the power, and which is the high power depend on the power dissipation of the PCBs. We have to place it accordingly. So these heat flow will be happen to the thermal pad and copper pucks. We have used the techniques over there. So now, so here the ambient, this is the set of PCB for your explanation. This is the way we have placed it. On the right hand side, this is the enclosure, which is aluminium, and where the yellow highlighted area we have placed the thermal pad and copper pucks, because the copper having a high conductivity, and it distributes the power. If the component is 5 by 5 mm, we applied the thermal interface material, and we place the copper puck over there. Then we have attached to the heat sink, so it will transfer. We have defined the proper heat flow path over there. So here the PCB with the source. These are the areas in the PCB which are highly heat dissipating thing. So red highlighted one. So all the highlighted areas are the power values we have applied using any type. We can use a source, or it's a 2 resistors, or you have a proper component material stacker. You can use that inside it. So from that, so here we have done in two things. One is a free as well as the forced convection. For the for the forced convection, this is the result. So we have for 55 degree ambient, it reaches 117 degrees Celsius. The same I have explained smart project system, right? We measured experimentally, making the point and probing the temperature everywhere. It 95% matching with our simulation and experimental. The similar way, this also we are trying to make with the experimental thing, because it's a complex PCB stake up. Be difficult to measure those temperatures. So that's why I have put the another upcoming slide. What is the tools and why simulation is needed? So that why I arrived to that point. So here the air is flowing. You can see it in the down picture. So here the overall system temperature is 170 degrees Celsius. On the heat sink, we have the temperature of 95 to 100 degree. So inside each PCB, the temperature, the maximum is on the one board. I didn't mention the name of the boards for the privacy. So here there is only one component which creating a more heat spot. I try to reduce over with the copper pucks, even with the heat sink over the top. So there is no such distribution over there. There is no already. This is already designed board, so we can't play it. That's why I said we have to start from the PCB level where we are going to assemble it, and how we can distribute the power. So this is already designed board, already made the assembly. Now I am reiterating it. The further how I can reduce the temperature, the way I can help to them. So here there is no way to reduce because of the size constraint as well as already designed one. we could not simply throw all the boards and redesign it. So our aim is to, with the existing assembly set of assembly, how we can reduce the temperature and what is the temperature. So here the maximum temperature is on one board, which we have highlighted. That also under the limit after placing the heat, changing the heat fin height and material over there with the proper thermal interface material. So other boards are and all within the limit of 100 degree Celsius. Only one board reaches the temperature of 115, 117 here. So these two result is for forced convection. So if it is a natural convection, if you run with a natural convection, the temperature reaches 133 degrees Celsius. So you can see the difference between forced and free convection over here. So these and all, these iteration and all in experimental, it is difficult placing one and all, and the complete design cycle and workman hours, it took more and more. So here the simulation works, and we have achieved it. This is the first connection for 1 meter per second. So here in the last in this three case studies, the first case study we have used a 5 meter per second condition force convection. The second case is the fan curve we have used. This is the 1 meter per second force convection on the enclosure. So now we come to the tools. So we have the two set of things. One is the simulation, another one is the thermography. Thermography is nothing but experimental. Simulation is experimental. We have to place the board over there over the cam. So depending on the temperature, it will we have make a contour and identify it. In simulation, we can probe each and every component. So here I have mentioned, I written the line. There is a no replacement for physical testing or experimental. So we have to do experimental, but where simulation play a role? If you have a proper input with the number of iteration, number of ideas you have, you can implement easily when compared to experimental. Suppose you are we are start from the dimension or placing the components, what type of material and what type of cooling we have to use. So those difficulties we can avoid using a simulation with the proper input, because simulation is nothing but whatever you are giving in, it will give out. It's just an equation to solve it. When the skilled person will do some additional work which will expertise in that particular area, will help on it. But in the thermography, you can take only the outer look, you can take only the case temperature, you can't iterate it with the experimental with the minimal time and minimal cost. It will end up in a huge cost over the time. So this is why the experimental and simulation is needed from us. Once we achieved, even we are doing a simulation, finally we can verify with the thermography or with the thermocouple or any kind of experimental thing. So all our ideas and all our iteration, we have to do it in a simulation, and finally we experimental it. It will reduce the overall cost with our technologies. So now the final slide will be the benefits of the thermal simulation. As I have mentioned, in the simulation we can involve all type of conduction, the convection, conduction and radiation, because if it is exposed, the last 5G unit is exposed to the solar. Exposed to the solar, you can't measure inside the lab with the experiments. You have to expose it. So those conditions and all we can implement in the simulation. The second one is the changing material. I have used the aluminum for that. With some combination, you can see it for a different combination or different high conductivity thing. For example, copper you have to use. If you are making the thing itself, taking a cost and time. So here just changing the material properties, and you can see which one is optimized for our enclosure. The third thing is what type of cooling we can account it. As I have said, one will be the liquid cooling heat pipe I have used for the projector, and another one is forced convection. Only we have to use free convection, not fit for that. And how we can distribute the component, where is the hot spot, how the hotspot we can remove from that thing, how to define the heat flow. These are the things. When we come to the system point of view, finally we can avoid the thermal shutdown. We can avoid the material that is a component failure and component overheating thing, a desoldering kind of a thing, material deterioration, and all the components, whether within the limit or not, in a complete system assembly. Finally, the warranty cost. How reliable your system is, that is our final objective. How long we can use the system. So already we have said 55% of the failure because of the temperature. So once you accounted all the things, automatically our lifespan will increases. Yeah, this is the end of the session. We have reached it. Thanks for all the people for your time for spending with us. Hope you enjoy the session, and if you have any query, you can type it in chat box on your thing, as well as you can mail me over this mail ID. I will note again. I will show. So before that, we are conducting the same time in the next month on 29th of September. HGI technology or a DDR X technology based on our LinkedIn. So you just visit our LinkedIn, make a pool, and you can happily attend and get a knowledge of this, which, whoever is needed. So thanks once again. Thanks for all. Thanks for your time.
Thank you, Arun, for that nice presentation. As you can see from the presentation that there are a lot of things to watch out when we are dealing with thermal management, just like signal integrity. Our engineer, Mr. Raghavendra, had the first session, and it's in line with that. Arun has given the other aspect of thermal management. Based on the webinar, we are aware that there are so many things to watch out and so many benefits of doing things the right the first time. Now I will open the session for question answers. So the first question, Arun, can you take it? Just a second, there's an issue with the new speaker. Arun, can you take the first question?
Yeah, yes. What is the accuracy that we can able to achieve over the simulation by Govindraj? Hi, Mr. Govindraj. The accuracy here, the simulation is, as I already said, it's depend on the input. If your material properties, your ambient condition, and your power dissipation values are perfect, you can definitely achieve the accuracy of 98%. So nothing in the world is 100%. 98% it is achievable. Through the simulation, and we have verified it. We have verified in the second case study and first case study with that experimental thing. So we have achieved it. So only thing is we have to take care of material properties, what we are getting, and how we are replicating inside the simulation, because the actual model, how it looks, the same model we are taking to a simulation or not. So that's the thing. Yeah. So thanks for the question.
Next question from Rakesh Babu. Arun?
One second.
Yeah.
You
can read out the question, Arun, so that everybody else also can hear.
For a system level thermal, how to idealize the complex components such as power supply, transformer, inductor, etc. So yeah, Rakesh, it's a nice question when we are replicating it in a model, in the thermal model. So here we have to apply power in a three-way. So one is a lump sum model. So which one is the, for example, we have the components of copper as well as metal over there. We just take the conductivity, cumulative conductivity of the particular volume of the thing. After calculating the conductivity value, applying conductivity value for those metals as well as the copper, then what type of dissipation it is for the whole individual thing, you just split it up and we can put it. So we have to make some approximation, because all the data we couldn't get it from the data sheet. So we have to do some iteration with that. So once you have done implementing those power values and the metal properties value, you can check with that experimental. So here with the thermography, whether we are reaching it or not. So if you are deviating, how much we deviated from the thing, we can able to achieve it from that. Yes. Thanks, Rakesh. Thanks.
The next question is from Rajesh Kumar.
Yeah, ma'am.
The question is there any correlation or ratio for power dissipation and power consumption to decide whether we go for thermal or system management? Whether we go for system level management. Sorry.
No. So it's not only what is his name, ma'am?
Mr. Rajesh Kumar.
Rajesh. Hi, Rajesh. So here there is no such correlation. It's totally depend on a flux. The same if the value looks higher. So first thing is we have to consider the power dissipation. How much dissipate? Because that only converted as a heat. That is the first point. And the second thing is, even if the dissipation is higher, if you distribute those flux to the complete area, suppose the component having 1 mm by 1 mm, having a power dissipation of 10 watt, the same 10 watt which is applied to a 10 mm by 10 mm, the temperature will be the different because we are distributing the heat flux. So that will only decide. We have to go depend on the heat flux values. We have to think of it. So better how much heat flux it comes from the PCB thermal point of view. So with that we can easily identify these are the highly heat spot generating area. So we have to do for a we have to account a system thermal over there. Thank you.
And the next question is from Mr. Harish Ranjan Singh.
Okay.
In the PCB design simulation, do you use SPICE model for component simulation?
Yeah, this the SPICE model and all they will use in PCB SIPA analysis. So I'm not a electronics SIPA expertise over there. But you drop a question over this mail ID, we will reply with our SIPA engineer. So who has conducted the simulation in the last previous session? He could have answer better for the SPICE model. You just drop your question to this mail. I will forward to him. Will answer for that. So here we are not using any SPICE model. Here it's a completely CFD solution. It's a computational fluid dynamics. We applied power. Those power values will placed as a heat source, and we solve the energy equation, continuity equation, and momentum equation here for our force convection, and take out the result over there. Yeah, thank you, Ranjan.
The next question is from Rajesh Kumar. He says for PCB level, what is good guess of heat flux to decide on?
Good thing is what is the power of the component divided by size of the component. But there is no such correlative graph over there. But only with our simple, if it is a single component, it's fine. We can define it using our heat transfer book, the Sengel. Everybody has explained it through the conduction. Because if it is a normal convective part, doesn't play much role. We use a conduction equation with the power flux value. We can take out this much heat will. This is the temperature I can arrive from that using that. But for the complex PCB, whole PCB kind of a thing, there is a n number of components. Better you go for a simulation to get it. They can easily identify from the simulation. You can easily identify with where those fluxes with respect to the power values are coming. The flux is nothing but area, the power applied divided by area. That's it. Yeah, thank you, Rajesh.
Any more questions? Anybody has? Yeah, you can, Rajesh, you can send us the email ID and we will share you the presentation slides. In fact, we can share the recording also.
Thank you.
If no more questions, okay. If there's no more questions, we will end the webinar. And thank you very much. And we look forward for your participation for next month. Depending on what the input is from the, from all of you, we will decide either it's a HDI technology or if it is DDRX technology. So give us your feedback and give us a feedback on the webinars that we are conducting through the emails that you are, the feedback email. So, and also if you all want a recording of the slides, we will be gladly sharing it to you. Thank you, and I'll again, thank you for your participation, and I'll just exit the webinar. Thanks.